All right, anybody? That hurt all my joints. We learned how to name covalent molecules, and we learned those rules a long time ago. So today we're going to talk about their structures. Covalent molecules are different than ionic, where ionic is always a crystal. Covalent molecules have a kind of myriad of different shapes and possibilities for them to combine and make different sort of structures. And so that's the more interesting part about covalent molecules you don't get with ionic, is that they can be more than just like a block or a solid cube. So anyway, and that gets down to we have to draw their shapes first today in 2 dimensions. We'll probably continue that on Thursday, and then on Friday we'll look at the 3-dimensional shapes and then bust out the molecular model kits and kind of take a look at the different possibilities for 3 dimensions. So, yeah.
Did we win the bouncy ball for the day?
No, we didn't.
48 was something.
You purposely did that though, so we lose.
Well, you cheated, so
What did I cheat?
you can't even say it with a straight face.
Who won
Where's the
that?
ball?
Hey, sorry.
Anyway,
Who won?
I don't know what's back there. We can talk
The
about it
Decker
later.
boys did.
Yeah, you guys.
The Deca boys.
Valence electrons are the ones that we care about, and those are the ones that are going to bond and be shared for covalent compounds. They're shared instead of donated for ionic compounds. And so that provides the shapes that we're going to examine today. So, we look at those shapes in something called a Lewis structure, which I think you've seen bits and pieces of before. A Lewis structure is a structural formula in which valence electrons are represented by dots. Good, A-Rod?
Yeah, right.
You've seen Lewis structures before. I think I've drawn them for you, I think the first data section, but have to get to drawing them yourselves today. In Lewis structures, dot pairs or dashes between 2 atomic symbols represent pairs in covalent bonds, and then draw a bunch of them for you in a second. Remember that to be a stable atom, you have to have how many valence electrons? 8. So everyone's going to share to get 8. The octet is the stable number of electrons that you want. And we're going to share electrons now to get 8. So there's lots of possible ways to do that. I'm going to show you that in a second. Tendency of bonding atoms to have octets, valence electrons, called the octet rule. Yeah, okay. All right, so I don't know what this says. Let's see. Okay. We'll use chlorine as an example first, and then I'll start drawing on the board. When 2 chlorine atoms form a covalent bond, each atom contributes, as Mark Wheat would say, 1 electron to a shared pair.
Okay.
Good job. Yeah, we can expect already.
Yeah, we did some of this already, a little bit. We'll draw it on the board, and so it'll be less abstract in a second. But just to give you an idea, since the picture's already here, each chlorine atom, if you look in the periodic table, brings 7 valence electrons to the table to kind of bond with. All right, so this one's got 7. Let's say this top one is its, and this one also has 7. Let's say the bottom one is its 7th electron. And so they're going to share those 2 electrons in the middle. When they share that pair, then they have 8.
You're on camera.
Oh, Deca.
Okay. Been there since like 7.
Thought for sure I would get one of those cookies, but
Huh?
You brought cookies.
So, are you going to speech today?
anyway, so they share a set of electrons in the middle, and that's how they get their 8.
No, your mom was
go
going
back.
Other way.
Other way.
Other way.
Keep going.
Keep going.
There
It's
It's like really
There's a bullet point on the middle of your forehead.
You're laughing about it.
You want me to go stand up there so you can laugh at me?
An unshared pair are the electrons that don't bond. So this is a shared pair right here in the middle. We can probably represent that with a line instead of those the two dots. But then all of these that are not bonded to anything else, these whatever 12 electrons there, those are called unshared pairs. The majority of it's going to be on the board in a second.
Can I please stand up there so you guys have my future there?
No, I don't want you to do that. Please stop. Single.
I'm not doing anything.
Single bonds. Where you share one pair of electrons, but you can have double bonds and also triple bonds, and I'll explain those again in a second. The electrons can pair in any order. The unpaired electrons usually filled in to show how they share electrons. So here, hydrogen and chlorine are going to share a set of electrons right here, and then chlorine has these three unshared pairs, which we'll get to right now. These three don't pair with anything else, but we still draw them to show that they're there. There's a set of rules on page 201 that I'm going to just kind of reiterate for you on the board, but and you can write them down if you want. I would suggest doing that. But if you don't want to, you can use the rules there on page 201 to show you how to draw these. That's the interesting part. Question. Go ahead.
Wouldn't 1 plus 7 make 8?
It does.
But why is there not 2 dots right there?
That they were sharing. The line represents two dots.
All the line represents 2 dots. Okay.
Okay, so here's how you draw Lewis structures. This I would suggest writing down somewhere safe, like your diary.
Problem A.
No, we're not doing sample problem A. It's too difficult for sample
Can we
problem
write it for sample problem A?
Sure.
Brian Lewis.
Again, the rules are on page, what did I say, 201? But I'll reiterate them here. The first step is to total the number of valence electrons. Secondly, you need to arrange the atoms in some sort of order. And I'll explain. This is kind of the step that is the most nebulous, I guess, and it has many possibilities.
Bless you.
Thank you.
Do you have gum?
No. God.
There aren't a lot of rules to arrange the order. Symmetry is one. Things in nature tend to be symmetrical, and so as you're drawing, you're putting all the atoms on a piece of paper, trying to make it symmetrical in a way. Another tip is that hydrogen will always be, hydrogen's never in the middle. It's always on the outside.
Does number 2 say symmetry helps?
It does. So hydrogen's never never in the middle, and symmetry helps us with the two tips. I can give you different arrangement atoms. And you need to distribute the number of valence electrons, or we're going to call them dots. I'll show you in a second. So distribute the dots. And you have to do that in a way that everyone gets how many dots do they want? How many electrons? 8. Except hydrogen will get 2. That's the only exception. Distribute the dots. Everyone gets 8. But hydrogen gets 2.
So that's all that hydrogen can have?
Yeah. Yeah. Because it only has a 1s shell, and the 1s can only hold 2 valence electrons. Finally, you can check your work. Check.
What is DOS mean? The?
I have no idea.
DOS boot?
These two things need to be true, and so you can always go back and look. Everyone has to have 8 dots. Hydrogen always gets 2, and you can only use a certain number of dots. So that doesn't make sense. It will in a second. We'll use chlorine as an example just to kind of refresh your mind. But if those two things aren't true, then you didn't do it right. For example, if you give everyone 8 dots, but you're only supposed to use 14 dots, and you use 16 dots, it's not going to be right. So that's the kind of thing you should look for. So let's start with chlorine. Chlorine is this. Now, for something that only has 2 things, it's a very simple arrangement. It's only going to be, they're only going to be ever next to each other. Like that's the only possibility. It's only 2 things, right? Now, when you total up the valence electrons, you should get a periodic table at this point, I guess.
Oh, okay.
Or you can look at this one. But as you're getting your periodic table out, chlorine has how many valence electrons? 7, and there are 2 of them. So this picture, when it's done, how many dots is it going to have? 14. Okay. The electrons are represented by dots. Each chlorine brings 7 dots to the table, electrons or valence electrons. So we're going to have 14 dots total. So when this picture is done, each of these chlorines has to have 8 dots, and I can only use 14 dots to do it. That's kind of the rule here. Okay, so I would, when I do these, there's no real, it's sort of a trial and error process. But I always start by just making a line and say, okay, they share at least one set of dots right there. Okay? That's their shared pair. One line equals 2 dots. Nice. And you can draw, if you want to draw 2 dots, then that'll be fine too. That look funny. Anyway, so they share a set there, and I'm going to fill in the rest and see if it works. And so each chlorine has to have how many dots total? Well, they bring 7. Well, when they're done bonding, how many are they going to have? 8. So I'm going to fill in the 8 right now, and then see if it works. So I'm going to give each of them 8. And if I used 14 dots, then I'm good, right? Because this chlorine, if you look, this chlorine has 8 right there. This chlorine has 8 right there. So that part works. Now, did I use 14 dots? Well, this is the part you go and check and say 2, 4, 6, 8, 10, 12, 14. Super, it works. Okay? So you don't need to draw the circles. I'm just showing you sort of like a Venn diagram. This is where they share the set of electrons. This is the electrons they don't share. But they each bring 7, and when they're done bonding, they're going to have 8. That's how it works. Except hydrogen's going to have 2. Pretty sweet, right?
Super sweet.
Try another example. So this is the simplest kind of arrangement, obviously a linear 2 things. But you could have more than 2 things. You could have, I don't know. Let's
3
say
things.
it was CH3Cl. First of all, what do you want to do?
Get the elements down.
Well, total number of valence electrons, let's add them up. How many does carbon have?
4.
4. How many does each hydrogen have?
2.
1. This is the part where they, how many do they bring?
1.
So 1 times 3. So 1 times
7.
3. And then how many does chlorine have?
7.
7. So we're grand total of 14. It won't always be 14, they just happen to be, these two are 14. Okay, so I want to arrange them in a way that, again, we try to use some symmetry. Hydrogen can't be in the middle, so either one,
Carbon.
chlorine or carbon has to be in the middle. Now, another thing you could write here is that carbon is almost always in the middle. That's another useful tip. Okay. You could draw this chlorine in the middle, you could do it right, but in this case, carbon is going to be in the middle. So, I've got carbon. Now you can kind of imagine every one of these atoms except hydrogen has kind of 4 spaces around it that you can put stuff. Okay? You can either put, unshared electrons, dots, 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 or you can put bonds. So what I'm going to do is I've got 1, 2, 3, and 4 things. So I'm going to put those 4 things around it and see if it works. So 1, 2, 3, 4 like that. Doesn't matter where you write them. I'm going to write my chlorine there, my H, my H, my H there. The last thing you do is fill in the dots and then see if you use 14. That's how I would do it. So which one of these needs more dots? Carbon's got 2, 4, 6, 8, right? So it's good. How many does hydrogen have? It's got its 2 here and 2 there and 2 there. It only needs 2. But chlorine's only got 2. So I'm going to fill in the dots on chlorine
5.
and say, 1, 2, 3, 4, 5, 6 there. Now chlorine's happy.
Oh, I was going to say, that only need 5?
No, remember it brings 7 to the table. When it's done, it's going to have 8. Okay, it's like it's a kind of before and after picture where you say,
I get it.
I have 7 valence electrons to give to this meal, and when I'm done with this meal, we will all be full
With 8.
8 or 2 if you're hydrogen. But I only brought 7. It's kind of like sharing. A potluck. It's like a potluck dinner. It's like a cross-country potluck dinner. Anyway, so now you go back and check to see if you have used the requisite number of dots. How many was I supposed to use? 14. So I got 2, 4, 6, 8, 10, 12, 14. Okay, so that part's good. Does everyone have 8? Yeah, chlorine's got 8. Hydrogen or carbon's got 8. Each hydrogen has 2.
Let's do it again.
Remember, these 2 things have to be true for you to do it right. Everyone gets 8, and you can only use 14 or however many dots you're supposed to use to make it happen. Okay. And again, it's part trial and error. So if you put chlorine here and switch where the carbon is, that'd be fine. It'd be fine in this case. But that doesn't always work. If you make something goofy, I could have used 14, let's say, no, never mind, that's not a good example. But you can, it's very easy to fill out one of these categories and forget about the other one. But remember, both of them need to happen for this to work. Can I do another one? Yeah. I'm going to.
Do it.
Okay. We're gonna step it up. I'm so crazy. What are we on example 3? Let me get an example to make up for you guys. I can't let you someone. Okay. Okay, great. No, let's not do so many H's. So stupid.
Let's do.
Okay, arsenic trifluoride.
Yeah, that's what
Everyone's favorite.
Perfect for a potluck.
For potluck. How many does arsenic bring to the table?
6.
6 plus 3 times whatever fluorine is. What's fluorine?
7.
7. So 6 plus 21 equals
28.
28. I'm going to use 28 dots to make this picture happen. Now,
That's crazy.
it's craziness.
Hey,
Arsenic's
only
only
5.
Arsenic's only 5.
Thanks, Corey.
1, 2, 3.
Yeah,
it's only 5. Good job.
That's not true. It can't be true.
Yes, it's true, because it's only 5.
But 5 plus 21 is 26. 5 plus, oh yeah, you're right.
1 is 26.
Yeah, that's better.
Yes, you can.
I like it. Okay, there we go. Better.
Testing you.
Yep, tested. It's important. Okay, when you arrange them, what'd you put in the middle? Yeah, pick the odd man out and put that in the middle, and you can arrange the 3 fluorines around it somehow. That's what I would do. This is why I say where symmetry helps. Okay? I would take the one that's by itself and put that one in the middle, so like this. Now remember, imagine each element kind of having 4 spots to put things, right? Top and left, right, and bottom. And so it doesn't matter where you put these fluorines. I'm going to put them across the top here like this. I should put it on the bottom, just make more space for us. And fluorine, and fluorine. And I fill in my bonds first and then see if it works, okay? And sometimes it does, and sometimes it doesn't. And I'll show what happens when it doesn't work. But this one's going to work out just fine. So I've got the 3 fluorines. I would also need to fill in my dots, because right now they don't have 8 electrons. So let's fill in. Okay, arsenic, so I'm going to put 2 dots right there. And then each fluorine is going to need 6 more dots, right? And then if I do this and it adds up to 26, I'm done. Because I've given everyone 8 dots, and hopefully I use 26, and then I go back and count. So I say 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. Hey, guess what? It worked. Ow, it's like magic, but not magic. Okay? So arsenic's got an unshared pair here that it doesn't use, and then this is what the fluorine looks like. Now, we're going to take these kind of abstract random pictures and then go on Friday and show you how it works in 3D, like what this actually looks like in 3 dimensions, because on a piece of paper, it looks very different than what it really is. Let me show you something else that kind of causes some problems. I'm going to pick one that works here. Like, in a second. Just shut up for a second.
Good job, I think I know
No one? Okay, you can have double and triple bonds as well, and that is where you kind of run into problems sometimes. So let's do. Oh man, come on. Oh, good. No, I want that one. Oh.
Let's do calcium.
I can't any of these.
Lithium nitride.
Alright, let's do carbon dioxide. No, it's not carbon dioxide. It's going to confuse you. You're going to get mad at me.
Can
Let's
we-
do nitrogen, dinitrogen difluoride, N2F2. Whoa. What?
I said woes.
That's
woes.
great.
First, total up your valence electrons. Each nitrogen is 5, right?
Yep.
5 times 2 plus 7 times 2.
Yep. What do they call
Is
it?
that a million? 24 again? Okay.
No, it's 26.
Wu-Tang again. Now, another thing that I forgot to tell you is that halogens tend to be on the outside. Which ones are halogens?
The ones that have 7.
Oh my god.
Two.
Are you serious?
Yeah, the ones in 7, the second last column. So I'm going to put the fluorines on the outside. I'm going to arrange them. Symmetry is important. I'm going to arrange this in a line. It's going to go like this. N and N and F. And F. This is the only way that works? Probably not, but this is the way that I'm going to do
Can
it.
you
So
stagger?
I wouldn't stagger them, no, again, because symmetry is what's important sometimes. And so we want N, F.
Sometimes, but not really, but
Six.
almost.
Okay, so I've already got 6. Let's fill in all my dots. What I do is I'll give everyone single bonds, fill in the dots, see what happens. Okay, so 1, 2, 3, 4, 5, 6. Like this, and this, and this. Everyone gets 8 dots. Everyone's very excited about it.
Doesn't work.
Does it work? Okay, so count the dots now. 2, 4, 6, 8, 10.
Whoa.
2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26.
Oh no.
So I've used too many dots. What you do is when you use too many dots here, you consolidate dots into a double bond instead of having a single bond. So what you do for a double bond is you erase, doesn't matter, well in this case it probably doesn't matter where you make a double bond. I'm going to make it in the middle, but you can certainly make it here or here, but and I would count that, right? When you make a double bond, you erase a set of electrons using your finger like I do on each side of the bond and then add a line. So you're saying the electrons that were here and there are now shared between them, and now you'll end up with your correct number, I think. You go 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So if you have too many dots, you can make a double bond. You want to see another example?
No, I got it.
We're going to.
So that counts the 4 with the double, that counts for 4, right?
Yep, that's 4 there. Yep. And instead of being here and here, we're just saying they're going to share that set, each of them.
Yeah, but the way it counts it.
Last example, maybe?
Sure, why not? It's a cougar day.
It is?
Yeah, we have no idea.
What's this thing called?
Carbon
Carbon monoxide. Delicious.
Carbon.
How many dots does it have?
Delicious.
4 plus 6, yes?
11.
10's these dots.
12.
Again, best thing to do is start with single bonds every time. So just go carbon and oxygen, dots, 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 fill in your dots.
GQ doesn't work too.
And you'll notice that you've got way too many dots, right? How many dots am I supposed to have? 10. How many do I have? 2, 4, 6, 8, 10, 12, 14. Yucky. So let's make a double bond first. Erase one and erase another. And then double bond. And now I've got 2, 4, 6, 8, 10, 12. Still too many.
Like a triple bond.
Triple bond, yeah, you can do it. Let's go crazy. Triple bond. Erase. And erase.
No way.
It
That
happens.
is illegal.
Buzzer.
Now I've got quadruple bond.
Oh.
10, 4, 6, 8, 10.
Yeah, draw
Notice that even though I made all those bonds, how many does this oxygen have?
11.
8. And how many does this carbon have? 8. Okay, so it still works out. Both things are true.
Work.
It works. This is always, I would just kind of, you don't have to memorize a lot of these, but this is one I would commit to memory. That is a triple bond, it's kind of a famous triple bond, as well as nitrogen.
Triple bond.
I just remember that, triple bond. There are, I don't know if I ever told you this, but there are 7 elements that exist as diatomic in nature. So for example, when I say oxygen to you, what do you think in your brain?
Oxygen.
Air.
That formula for oxygen.
O2.
That's the formula for oxygen, right? Because in nature, oxygen is more happy to be bonded to itself. There are 6 other elements that are like that. I probably should tell them to you right now. They're very easy to remember. They're called the sneaky 7, or the stairway to 7, if you will. Or that's all I got.
Catchy.
Anyway, so they're very simple to remember. They start at nitrogen element number 7, and they make a 7. So they're these, and then this one right here. So nitrogen, oxygen, fluorine, chlorine, bromine, and iodine, and the odd man out is hydrogen. So start at 7, make a 7. These 7 elements exist in nature as diatomic. So when I say chlorine to you, you should think chlorine is what? Cl2. In nature, that's what chlorine gas is. Okay, I would have to say elemental to indicate that it's just by itself, but in nature, all those are bound to each other
What's the stuff in pools?
for increased stability. Chlorine.
Just say no.
Well, it's in.
A solid one.
Yeah. Well, no. It's
Yeah, the solid.
I think they use like a.
The liquid and solid.
It's probably not.
It's a gas.
Yeah, chlorine is a gas room temperature, so it's probably some sort of compound that it contains chlorine. I don't know what it is.
Which also doesn't kill you when you breathe it.
Good, important point.
It does kill you.
You should practice some of these. Let's see. I'll find some for you.
It's like a little thing.
Summer's a cougar day, be nice.
It is.
Yeah, we have about
Where's your
2
summer?
hours.
We don't need any more work.
We have to play COD.
Yeah, we got summer.
What's formation? Formula.
You have like 15 minutes to do it.
Or electron.
Page 202, 1 and 2. Back for sure.
Sure.
Summer's like soul chemistry.
Page 205, 1 and 2.
I told this about your live. I
Stole it online.
Usually to
Well, like, I need chemical.
What a loser.
Hey, Cody, you know you can spell your name out of elements?
I can also spell bad words.
Stop it.
Oh, there you go.